Here. We've been talking chapter 8, and we've talked about, again, really two types of formulas, our empirical formula and our molecular formula. Excuse me. And yesterday, we kind of went through the steps of calculating an empirical formula. And again, this is a situation where you would not have necessarily the molecular formula given to you, and you want to calculate the empirical formula. So a couple of things that very commonly you are sort of starting with the empirical formula is the percent composition by mass that we also talked about last time. And basically, to calculate the percent composition by mass, you take the mass of the element you're interested in, and you basically take the molar mass of the compound, and you times it by 100%. So again, we can figure out the percentage by mass of each element in a particular formula by doing so, basically figuring out how much of each element's present and divided by the molar mass of the entire compound and times it by 100. Now, that's usually a lot of times a starting point in an empirical formula problem. So remember that you basically just want to kind of turn your percentages into grams, or really whatever unit you're sort of given. You want to make sure that you kind of get each of the elements into grams. And again, if we do have the percent composition by mass, you could assume that you have 100 grams of everything. And what that does is it just keeps the percent numbers and the gram numbers the same. We then will take our grams and convert them to moles. And remember to do that. That's the molar mass conversion from the periodic table that allows us to do that. Now, at this point, you will have moles of each element that is present. We're going to then divide by the smallest number of moles. And as we talked about yesterday, again, it can a lot of times come out pretty good. For example, if you had, again, 2 moles of A and 4 moles of B, here from step number 2, we would then divide each of these by the 2 moles, which is the smallest. And we would get a 1 and we would get a 2. And again, if you do this step and you do really hit sort of whole numbers, are really, really close to a whole number and close enough to round, which again, typically speaking, does need to be pretty darn close to the whole number. That will be your empirical. Again, something like A2. As we also talked about yesterday, and as we saw, you won't always get nice, perfect whole numbers a lot of times, and sometimes you may get more of a decimal number when you divide. So again, if you had 2 moles of A and 5 moles of B and you divide by 2 moles, you are going to get 1 there, but you're going to get 2.5 here. And that again would give you an empirical formula of 2.5, as we talked about. These numbers on the bottom, which are really the moles, they do need to be whole numbers, so you can't have any decimals. So here at 0.5, and as we talked about yesterday, and as we saw, I think in one of the examples, a very common ending is 0.33. These are considered too far to round up or down. So a number to sort of correct it. And again, here, if you just say 2.5 times 2 in this case, that will give you a whole number of 5. We do want to actually multiply our empirical formula by the factor of 2. And we do want to multiply everybody by that factor of 2, not just the one that needs it. And that would give us, again, our proper sort of empirical formula in this case. Any questions on those steps there? All right, so we did an example last time, so I think maybe we're at this example. So why don't you give it a go, take a few moments, and we want to calculate the empirical formula in this situation. Sulfur is 3207 on the periodic table, and oxygen is 16. So take a few moments, calculate the empirical formula, see what you come up with. It's just given to us, but we do have grams of each element, and we do have the kind of total mass of the compound. And what we want to make sure is in this situation, kind of like what we want to make sure of when we have percentages that they kind of add up to 100. In this particular case, we want to make sure when we sort of add these numbers together that we do get this number here and we're not missing anything like an element or anything like that. And in this case, we do get the total mass there of 1.078, which is made up of 0.54 grams of sulfur and 0.538 grams of oxygen. So once we sort of make sure we're not missing anything, and by the way, if you were obviously, you could add up those grams, the 0.54 to 0.538, and subtract it from the total mass there, and that would give you the mass of the missing element. Very similar. If you added up your percentages, they didn't equal 100%. You can subtract from 100 and get kind of the missing percentage of what's there. And again, that sometimes does occur. Obviously, it would probably mention something like there's another element involved as well, which obviously in this case, we don't have to worry about that. So we're just going to take our grams here of each element, and we are then going to do basically our next step, which is convert them into moles. And we are going to go to the periodic table there, and we got 3207 for our sulfur, and we got 16 there for our oxygen. And that's going to get us here 0.54 divided by 3207. Looks like a 0.016382. I'm just going to take it to a few digits. And 0.538 divided by 16, 0.033625 moles of oxygen. Once again, at this point, once we convert it into moles, we're going to pick whichever one is the smallest. And it looks like in this case, it is sulfur is the smallest. So we're going to divide them both by the moles of sulfur that we have. And that's going to give us a 1 there for our sulfur. And maybe we'll get a nice number, which I think we will. We'll basically get kind of like a 2 in this case for our oxygen. Again, on your calculator, you got something like maybe 2.05. Again, this is close enough to round to 2. Again, common ones where it's not, like I said, 0.33, 0.5 are very common sort of ones. So we basically hit whole numbers, so that would give us an empirical formula here of SO2. Any questions on that there? All right, so let's try another one here. The composition of this acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. What is the empirical formula? Again, carbon 12.01 on the periodic table, hydrogen 1.008, and oxygen 16 still. All right, so let's take a look. Again, we have percent composition by mass. Again, just taking a quick look at the percentages, they do add up to about 100%. So we're good. So with that, again, we could just assume that we have 100 grams of everything, and that's just going to keep the numbers basically the same. So that would mean then we had about 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Now that we have them into grams, we're going to convert them into moles using our molar mass from the periodic table. And again, we got our grams on the opposite location. So on the bottom, 12.01 grams per mole, 1.008 grams per mole, and 16 grams per mole. And that's going to give us our moles of each of these. So 49.3 divided by 12.01 looks like maybe a 4.1049 moles of carbon. 6.9 divided by 1.008, a 6.8452 moles of hydrogen. And lastly, 43.8 divided by 16, and 2.7375 moles of oxygen. Once again here, once we convert it to moles, we are looking for the smallest number of moles to divide everybody by. And it looks like in this case it is oxygen. So We're going to divide everybody by the moles of oxygen. I really butchered that number pretty badly. Let me try that again. All right, 2.7375 and 2.7375. All right. So we got one there for oxygen, for our top guy there. We got basically 1.499, which is about 1.5. And then we got 6.8452 divided by 2.7375. And we got about a 2.5 in this particular case. And that would give us an empirical formula here of C 1.5, H 2.5, and an O. And again, as we talked about, we cannot have decimals or half of things. And again, both of these obviously are too far to round. So we do need to look for a number we can multiply the entire thing by that will actually fix both of them. And in this case, a 2 would fix everybody up pretty good. So if we multiply everybody by 2, obviously when you do the 1.5 times 2, that's going to get you a 3. And our 2.5 times 2, which will give us a 5 in this case. So a 2 will fix both. And I would say you should probably be able to fix multiples with one number to do that. Again, we want to multiply everybody here by 2. And that's going to give us C3H5O2 as our empirical formula. Again, all whole numbers. The numbers on the bottom need to be. Any questions on that one there? All right. All right, now that we know how to calculate the empirical formula, let's talk about how we actually can calculate the molecular formula. So if you're asked to calculate both, which a lot of times you are asked to sort of calculate the empirical formula and the molecular formula sort of together, you basically need three things to determine the molecular formula. The first thing you need is the empirical formula. So you do need the empirical formula. Now, there may be problems where they may just give you the empirical formula, but I would say probably in most cases, you're going to have to calculate like we just did in all those previous problems. So a lot of times a molecular formula sort of problem is really just an empirical formula problem with a little molecular formula ending, basically. So if it's given to you, great, but most of the time it will not. So you will have to kind of go through the same steps we just did to calculate the empirical formula. Once you do that, you do need the molar mass of the empirical formula. So once you have the empirical formula, you also need its molar mass of the empirical formula. So once you have the empirical formula, once you have the molar mass of the empirical formula, the last thing that you need is the approximate molar mass of the compound you're trying to figure out the formula for. The good news on that is in textbook problems, that is usually given to you. So that's usually given to you in a problem. And somewhere in the problem, they'll say, hey, this compound has a molar mass of like 100 grams per mole or 100 grams or something like that. They may also, in addition, not necessarily give you just one number. They may actually give you a range, like, hey, the molar mass is between 100 and like 120 grams per mole or something like that. So they sometimes will give you a range of the molar mass, or they'll just give you a number. If they do give you a range, you could do one of two things. You can't, or I guess basically three things. You could either take the low end of the range that they gave you and use that number. You could take the high end if you want, or you could just average the two numbers and take something in the middle, and they will all pretty much give you the same thing. So once you have basically those three things, empirical formula, molar mass, and usually given to you in the problem, the molar mass of the compound, you're going to take the molar mass of the compound that's given to you, and you're going to divide it by the molar mass of the empirical formula. And that is going to give you a number. And that number is what you're going to multiply the empirical formula by. So that number you will multiply the empirical formula by. So let's just say your empirical formula was A2B5, and you did this little division thing, and you got like a 3 as the number. You would then take that 3 and multiply the empirical formula by, and that would give you A6B, what did I say, 3 there? 15. And that would be your molecular formula in this case. And I will say that we talked about sort of rounding with empirical formulas and numbers, and like you could only round if it's really, really kind of close. I will say that when you're doing this division here to figure out that number to multiply the empirical formula by, you could be a little bit more free with the rounding, and you may not always get like a nice, pretty number. So you could round a little bit more here to a whole number. So for example, if you divided that and you got maybe like a 2.1 or 2.2, which normally in like the empirical formula, that's like too far to round. Here you can round it. And that's because this number is based off of the relationship of the empirical formula. It's the simplest whole number ratio of what's present. And also the fact that a lot of times, or some of the time, the molar mass that's given to you in the problem is an approximate molar mass. It's not like the exact molar mass. It's not like a perfect number sometimes. And like I said, sometimes you may even have a range. So you could do a little bit more free rounding here to the whole number when you're doing this calculation than you can when you're doing the empirical formula sort of rounding. And again, you should be in good shape. Any questions? All that there. Now, personally, I think you should multiply it out, the number that you get, to give you a formula like this. I will say occasionally in books and stuff, you will see people kind of like put the empirical formula in parentheses and put the little number on the bottom, to indicate sort of molecular formula. I personally think, man, you probably just multiply it out and sort of get the number over there and stuff like that. But you will sometimes see that with parentheses and a number on the bottom. Sometimes books like to do that. All right, so let's take a look at one here. Give it a go. The empirical formula for acetic acid is CH2O. What is the molecular formula if the compound is, or the mass of it is approximately 60 grams? So give it a go again. Carbon still 12.01. Hydrogen. Okay, so let's take a look at this one. So remember, to get to the molecular formula, basically need three things. We need the empirical formula, we need the molar mass of the empirical formula, and we need the molar mass of basically the compound there. And in this particular case, they were nice enough to give us the empirical formula, so we didn't have to actually calculate it. Once again, if they didn't, you would need to go through those steps we did previously. This is the molar mass of the compound. And again, sometimes it will be written like that, 60 grams. Sometimes it will be written more like a molar mass, 60 grams per mole. So again, that's basically the molar mass there of this compound. So that means that really the only thing that we're missing to allow us to get to our molecular formula is the molar mass of our empirical formula. So we would take our empirical formula, which is CH2O. We would calculate our molar mass, so 12.01 for our carbon, plus 2 times our 1.008 for our hydrogen, plus 16 there for our oxygen. And that's going to give us an empirical formula molar mass of about 30.03 grams per mole. We again now have everything we need. So we're going to take the molar mass of the compound, which is basically 60 grams per mole. We're going to divide it by our empirical formula molar mass, 30.03 grams per mole. And obviously here we are going to get a number pretty close to a whole number. We're going to end up with 1.998. That clearly is close enough to 2 to round. And at that point, that is the factor by which we want to multiply the empirical formula by. So again, we're going to multiply everybody in the empirical formula by that. That's going to give us C2H4O2. And now we will have our molecular formula in this case. Any questions on those steps there? All right, let's try one here. We have a compound that contains 1.52 grams of nitrogen, 3.47 grams of oxygen. The molar mass of the compound is between 90 and 95 grams. And again, that's basically grams per mole. Determine the molecular formula and its molar mass to four significant figures. And again, nitrogen here is 1401 and oxygen is 16. All right, so take a few moments there. Again, three things you need: empirical formula, molar mass of the empirical formula, and the molar mass of the compound. So give it a go, see what you come up with here. Okay, so let's take a look. So in this case, again, we need three things to get to our molecular formula. We need the empirical formula, we need the molar mass of the empirical formula, and we do need the molar mass of the compound. Out of those three, we really only have one of them, and it is sort of a range here of 90 to 95 grams per mole is our molar mass. So we do need to calculate the empirical formula. So we're just going to go through the same steps that we did on the previous problems to calculate it. In this case, we are in grams. So we got our 1.52 grams of nitrogen, and we have our 3.47 grams of oxygen. Like normal, we're going to convert these guys into moles using the molar mass from the periodic table. And if we do that here, we will end up with 1.52 divided by 1401. Looks like a 0.1085, we'll call it, moles of nitrogen. 3.47 divided by 16, going to get us a 0.2169 moles of oxygen. We're going to divide by the smallest, which in this case looks like it is nitrogen. So we'll go 0.1085 and 0.1085 here. That's going to give us a 1 here, and I believe we should end up with a 2 there, basically. Again, a 1.999, which is basically 2, if you take the unrounded number. And that's going to give us an empirical formula here of NO2. Now that we've calculated our empirical formula, we will need now the molar mass of it. So that's the last sort of step thing that we need. So to get our molar mass of this guy, we got 1401 for our nitrogen. There are two oxygens, each at 16. And that's going to get us here a molar mass for our empirical formula of about 46.01 grams per mole. Now that we have the molar mass of the empirical formula and the approximate molar mass here of our compound, we could figure out our factor that we need basically to multiply our empirical formula by. Like I said before, here you do have sort of a range. So you could take the bottom part of the range if you wanted to, which is 90, and divide it by 4601. And in that case there, you're going to end up with about a 1.96. You could take the high range of it, which is 95 grams, divided by 4601. And that's going to get you about a 2.06. Or you can average the two numbers. 90 plus 95 divided by 2 puts you about 92 and a half. Would put you somewhere in the middle there, divided by 4601. And that's going to get you looks like a 2.01. So basically, with rounding, it looks like no matter which one you kind of choose, obviously here we're looking really at a number of 2 as our factor. So again, if you sort of have a range for the molar mass, you could do what I did there. You can kind of go low, you can kind of go high, or a lot of times people will just take the average value between the two numbers and kind of use that. That means that we are going to take our our empirical formula here and multiply it by 2, and that will give us N2O4 as our molecular formula in this case. And now that we do have the molecular formula here, we could get the molar mass of it, which is 2 times 1401, which was part of the question, I think, plus 4 times 16. And that's going to get us here about 9202 grams per mole, which is, kind of in the middle-ish value that we kind of took there along the way. Any questions on any of those steps there? Okay, we're going to continue on here. One more example. Let's do this one here. A phosphorus oxide contains 43.64% phosphorus and 56.36% oxygen. We're looking for the empirical and molecular formula. The molar mass is approximately 283.89 grams per mole. Phosphorus 3097, oxygen 16. All right, so take a few moments there, calculate it up. Okay, let's take a look again here. We basically need to calculate both. So we'll start with the empirical formula. And we do have our percentages given to us. It is about 100%. So we're going to assume 100 grams. And again, that's going to keep our numbers the same. So we basically will have 43.64 grams of phosphorus and 56.36 grams of oxygen. Like normal, we're going to now convert these guys into moles using the molar mass from the periodic table. So 16 grams per mole for our oxygen and 3097 grams per mole for our phosphorus. That's going to get us here 43.64 divided by 30.97. Going to get a 1.4091 moles of phosphorus. 5636 divided by 16. Going to get us a 3.5225 moles of oxygen. Here again, always divided by the smallest. And in this case, it is phosphorus is the smallest. And we're going to divide by 1.4091, it looks like, both of them. 1.4091. That's going to give us a 1 for the phosphorus. And for our oxygen, it is not going to give us a 1, I don't think. It's going to give us a 2.499, which is approximately 2.5. That's going to give us an empirical formula at this point of P1 O2.5, like we talked about previously. That is too far to round. So just like we saw earlier, a factor of 2 will take that into a whole number. So remember, we again need to multiply both by 2 to get us to a whole number. So P2O5 should be our proper empirical formula at this point. Any questions on that up to there? So now that we have the empirical formula, that's one of the 3 things that we need to calculate the molecular formula. So we have the empirical formula. We once again, for the molecular formula, have the approximate molar mass given to us in the problem. So the third thing that we need is the empirical formula's molar mass. So let's calculate that. We got 2 phosphorus at 3097. We got 5 oxygens at 16 each. Going to give us a molar mass for our empirical formula of, looks like about 141.94. And now we're going to take the molar mass of the compound and divide it by the empirical formula's molar mass. So take that divided by 141.94. 94. So 283.89 divided by, don't hit the clear button, try to divide again. There we go. And that's going to give us a factor of 2. By the way, it won't always be a factor of 2. Just hit a lot of 2's here. And once again, that number is what we're going to multiply our empirical formula by here. And that's going to give us a P4O10 in terms of our molecular formula. Any questions on that there? All right. Before we move off of this problem here and molecular empirical formulas, I do want to show you maybe just an alternative way that you can figure out the molecular and empirical formula if you do have the percent composition by mass given to you. So if you do have the percent composition by mass given to you, and you do have the molar mass of the compound given to you, and it's maybe not a range of molar masses, but you could probably still do it with a range. But if you have the number like we do in this situation, so in this situation, we know we have 43.64% is phosphorus and 56.36% is oxygen. And we know the molar mass of the compound we're looking for is 283.89 grams per mole. So you could actually, because this is the percent composition of each element present, you could actually convert your percentages into a decimal, divide by 100, or just move to decimal place, whichever way you want to do it. That would give you 0.4364. And if you do that for this guy as well, divide by 100 or move to decimal, you'll end up with 0.5636%, basically, convert into a decimal. We're going to actually multiply each of those percentages by the molar mass, 283.89 grams per mole, or just grams if you want to look at it at that point. So we're going to multiply each of them by that. And if I do that, 0.4364 and times it by 283.89, that would tell me out of that 283 or so grams, about 123.89 grams of it is phosphorus. And obviously that's the percentage of phosphorus, right? And that's oxygen. And if I do that, basically 56% or so is made up of oxygen. And out of that total 283 grams, that means there's 160 grams of oxygen in this case. So you can actually use the percent composition by mass and the molar mass of the compound and multiply them together. Obviously, you do need to convert the percentages into a decimal. And now what you could do is convert these grams into moles. And you could divide it by the molar mass of phosphorus, which is 3097. And you can also divide this guy by our 16 grams per mole. And if you do that there, take 123.89 divided by 3097, you get a 4. And if you take 160 divided by 16, you get a 10. And that is the molecular formula we just calculated, basically, because this is based off of the molecular formulas, molar mass. And that would give us a molecular formula, as we just saw in the previous calculation, of P4O10. And at this point, now that we have the molecular formula, we know that the molecular formula to the empirical formula is just reducing it down to whole numbers. And this is basically 4 phosphorus for every 10 oxygens. You could divide everybody by 2 and still get whole numbers. And if you do that, that will get you basically 2 phosphorus and 5 oxygens, which is your simplest whole number ratio of what's present. And you will have the empirical formula. So if you do have the percent composition by mass and the molar mass, you could actually tackle the molecular formula first and then just reduce it down to get to your empirical formula. So I would say, by the way, if you don't have the percent composition by mass and you have just grams and stuff like that, there's no sense in figuring out the percent composition. So it's just best just kind of do it the other way. But if you have this, you could go this way if you would rather. This also avoids, maybe figuring out the factor you need to multiply everybody by to get to a whole number on the empirical formula. Any questions on that there? Okay. So that wraps up this chapter. Questions, molecular formula, empirical formula. Clearly, you need to be able to calculate those things. Yeah. Okay. We're going to move on back to chapter 6, I believe. Okay, so chapter 6 is a very short chapter. It's really just about chemical equations and balancing chemical equations, which we kind of touched upon as we jumped to 10 and around a little bit in some of the chapters here. But officially in this chapter, we're going to talk about chemical equations and balancing. So how do we know, again, a reaction occurs? There's just several times, obviously, indications that allow you to know whether or not, maybe some type of chemical reaction has occurred. Sometimes a color change is indicating that a chemical reaction occurred. By the way, obviously, a chemical reaction is a chemical change, right? So we're producing new things than what we started with. A solid being formed, as we'll talk a lot about in a upcoming chapter. A solid is sometimes referred to as a precipitate, and a precipitate is sometimes abbreviated as a PPT for a precipitate. Bubbles being formed, and again, typically if we do some type of reaction and we see bubbles that are formed, that's usually a pretty big indication that you made some type of gas, and that's usually what is causing those bubbles that you see occur. Sometimes, again, some signs of chemical changes, heat or flame is produced. Clearly, flame you could see, but not visual heat exchange. If you're holding on to a test tube and it starts to get really hot, there's obviously some type of reaction releasing energy, right? And that's why your hand gets hot because you're holding it. It's an exothermic reaction. The energy is going into your hand and it starts to hurt at a while or at some point. Also, by the way, if you're holding, for example, a test tube and it gets really, really cold, that's probably also a chemical reaction happening because, frankly, it's sucking all the heat and energy out of your hand in an endothermic reaction, and it's sucking the energy from your hand, and that's why your hand feels cold. As you can see here, 9-volt battery going through electrolysis of water, which you will do, I think, in an upcoming experiment. All these bubbles are the hydrogen gas, oxygen gas being generated as a result of this chemical reaction. This is a titration, and a lot of times in a titration, we do look for a color change to indicate that a chemical reaction is over. Very common sort of titration procedures that we'll do, and we'll do it towards the end of the semester, is a acid-base titration, and as a result of the acid and the base reacting with each other, it will make a salt and water. The actual pH will change, and you usually put an indicator and the color will change to indicate that the reaction is over. Sometimes you could even do a titration like this and actually form a solid. As you're doing the actual titration and adding solutions together, you'll form a solid that will form as well. Here's the experiment up on top coming up here, 15, basically. Add a couple of solutions, get yellow solid being formed. And again, the formation of some type of solid that was not there previously is definitely usually an indication that some type of reaction has taken place. Obviously, more gas bubbles. That is actually a combustion reaction. Methane coming out of the pipes, a little spark and some oxygen. Obviously makes a flame, makes a combustion reaction that occurs. And that's some zinc with some hydrochloric acid. The bubbles that you see here is the reaction between the zinc and the hydrochloric acid. It is a type of reaction we'll talk about in chapter 7, I believe. Is a single replacement reaction. And what's happening here is the zinc is actually kicking up the hydrogen in the acid, and the hydrogen is becoming hydrogen gas, and that is all the bubbles that you see here. So one of the major ways that we represent a chemical reaction is using chemical equations. And in chemical equations, we use obviously the symbols for the elements to indicate what's going on. Remember that in a chemical reaction, the only thing that's happening is we're basically, again, breaking all the bonds that we're starting with, and we're making new bonds on the end of the reaction. And the formation of those new bonds will create new substances, and that is, again, a chemical change that occurs. Here we have hydrogen gas burns in air, which contains oxygen to form water. Now, one of the important things to sort of keep in mind is sometimes you will be asked in chemistry to write a chemical equation, and that will require you to use the proper formulas when you do so. And remember that we do have some diatomic molecules that are elements like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and so forth. So very common if you're given something in words, they may just say hydrogen gas plus some oxygen gas, or they may say molecular hydrogen plus some molecular oxygen are reacting with each other. And you want to make sure that you are using the correct formulas for those things. It's a super common error that people make if they were going to, for example, write this reaction from the words. A lot of times people will just write H plus O. It goes to H2O. And remember, the formula properly for hydrogen by itself or oxygen by itself is H2 and O2. So one of the very first things that you want to always sort of think about when you're writing an equation, if you are from words, is you just really want to get the right formulas down. And you don't want to worry about balancing the equation or anything like that. You just want to start with the right formulas. Because really, if you do not start with the right formulas, well, frankly, you might be there all day trying to balance an equation that will never balance at all. And we can read this equation a couple of different ways. Again, we could say hydrogen gas plus oxygen gas are forming or yielding water. Or we could say molecular hydrogen plus molecular oxygen is yielding water. To yield or to form is really what the arrow represents in the equation. And the plus sign means reacting with. When we look at the above equation, there's a couple of things that are maybe not so good. And one major thing is whenever we have an equation, it does need to be balanced. And we talked about it in chapter 10. We'll also talk about it here and coming up in a second. But when we do look at an equation like this, on the left-hand side of the arrow are the reactants. And on the right-hand side of the arrow are our products. And remember that the reactants really are the sort of starting material in a chemical reaction. The products are basically what is formed as a result of that reaction taking place. Now, one of the things that we must always have, because chemical reactions only involve breaking bonds and making bonds, and as we talked about in the bonding chapter, that only involves electrons. So that's all about electrons. And remember in an earlier chapter as well, the one thing in an atom in terms of protons, electrons, and neutrons that determine what element you're dealing with is the protons. And the protons in the nucleus determines the element you're dealing with. And because chemical reactions only involve electrons, they never touch anything in the nucleus. We never lose elements along the way in a chemical reaction. So however many, for example, carbons we start with on the left-hand side, we should have the exact same number of carbons on the right-hand side. They may just be in different things, but we should never, for example, lose carbons along the way. We also should never gain extra elements along the way in a normal chemical reaction. Again, because it only involves breaking and making bonds, has nothing to do with the nucleus, and because we don't change the protons, we never change the elements. So if we sort of add up everything that's going on here, and one of the good things to do, especially when you're balancing, as we'll talk about, is to make like a little table. And if we look on the reactant side and we look on the product side, and we just look at the elements we got going on, we can see on the left-hand side or the reactant side, we have two hydrogens and we have two oxygens. And once again, the number on the bottom goes to the guy to the left. On the right-hand side, we have two hydrogens and we only have one oxygen. So the problem with the above equation is it is considered an unbalanced chemical equation. Um, And we're going to talk about obviously how to balance it here in a second. But the one thing you should always remember is if you have a chemical equation, it always needs to be balanced. So sometimes they're given to you balanced, sometimes they are not given to you balanced. So one of the first things you should always look at when you come across a problem or anything like that that has a chemical equation is you should take a moment, just make sure the thing's actually balanced. Because later on in chemistry, you may do all these great calculations, but if your equation is not balanced and you need to do some equation work there from the equation, you will end up with the wrong answer. So how do we fix it? One of the other really important things to remember when we balance equations is the absolute only thing that we can change to balance an equation is the numbers that come in front, the coefficients. We never ever change any other number in a formula. We never change the little bottom number because if we do, we are changing what it is. So if I took the 2 out of the H2O on the bottom, that's no longer going to be water at that point, right? I changed it to something else, so we don't want to do that. By the way, we never put a big number in between of the formula, like between the H and the O there in water. We don't put like a big number or anything like that. So we can only change the coefficients there. And in this particular case, as we saw previously, again on the reactant side and product side, we have H and O. And again, we have 2 and 2 and 2 and 1. So obviously here we would need to put a 2 in front. And when we do put the 2 in front, it does count for everybody that's behind it. So it counts for each of the elements that are behind it. So that's 2 times 2. That now gives us 4 hydrogens on the right. And now we have 2 oxygens on the left. And as we will talk about, that is very common thing that happens when you go to balance an equation. You'll fix one thing, but frankly, screw up something else. And that's not a big issue because we could simply fix that by going to the other side. And also, once again, only putting a coefficient in front and putting a 2. And again, 2 times 2 here is going to give me 4. I still got 2 of those. And now I do have a balanced equation. Again, the only thing that we change are the coefficients that come in front. So you never ever want to change anything else. And much like most things in chemistry, like we see here with the O2, there is no number written in front, but it is assumed to be 1. So just like normally, we don't really write 1 a lot in chemistry. In front of that O2, the coefficient is 1, and we typically, again, don't write it. It's just assumed that there is a 1 hanging out right here. And again, not typically written ever when you're balancing an equation, just left blank, basically. Any questions on that there? So this represents, again, the balanced equation, which, as I mentioned a second ago, 100% of the time, you always got to start with a balanced equation. Otherwise, a lot of things could go kind of wrong for you, especially if you're doing calculations. We've sort of talked about the different parts of equation, but once again, everybody on the left-hand side of the arrow is your starting material. And again, those are what are referred to as being reactants. And a reactants is what comes together. And once again, on the right-hand side of the arrow, that again is going to be our products on that side, which is what is formed. That arrow is a one-way arrow, which indicates that it's just basically going from reactants to products here. So basically what's going to happen in this reaction, as I mentioned, all the bonds there on the left-hand side, they're just going to break apart. And simultaneously, if you remember from chapter 10, as they're climbing up that activation energy hill to get to the very top, they're going to start forming the new bonds. And they'll get to that transition state, which was at the very top, highest in energy. And then they'll come down to the other side in terms of energy and make your products, right? Like we talked about there in chapter 10. All right. Now, when we look at a chemical equation, there are several relationships that we could actually take from the chemical equation. And in the next chapter, we're going to talk about chapter 9. We'll talk about some of these relationships. But when you look at those coefficients that are in front, you got two and again a one and a two. You could say, for example, there's two molecules of H2 react with one molecule of O2 to form two molecules of H2O. The relationship that we definitely will use the most, and especially when we get to chapter 9 coming up, and this is used in what I refer to as stoichiometry problems. This is a mole to mole relationship, so we can actually look at the coefficients and say we have 2 moles of H2 react with 1 mole of O2 and gives us 2 moles of H2O. The last relationship we don't use all that much, but it is the idea of the law of conservation of mass. And as I mentioned a second ago, since we really don't change any elements along the way, in this case, we started with 4 hydrogens. We will end with 4 hydrogens on the other side. And since each hydrogen is like 1 gram or so, we got about 4 grams of hydrogen on each side. And we have 2 oxygens on the left, and we end up with 2 oxygens on the right. And once again, since each oxygen is 16, we've got about 32 grams of oxygen on both sides. Again, because we did not form or lose any elements along the way, the molar masses of all the elements on the reactant side should add up to all the molar masses of the products, of the elements on the product side. Now, obviously, there are some other information that we do commonly see in equations, and those are sometimes abbreviations that we see next to the formulas in a chemical reaction. So very common abbreviations, you will sometimes see an S, which represents solid state. That means that substance is in the solid state. You'll see an L, which represents that thing's in the liquid state. You'll see a G, which represents that thing is in the gas state. And you will oftentimes see an AQ that represents it's in the aqueous state. It's basically a solution. So it's basically something dissolved in something like water to make a solution. And those are very common sort of abbreviations that we do see in chemical equations. As you can see here, we got some gases going on, we got some liquids and gases and solids. Now, a lot of times we do write chemical equations to represent chemical changes that are occurring and chemical reactions that are occurring, but we also can use chemical equations to represent physical processes that are occurring. So, for example, if we look down here towards the bottom, we got basically water here in the liquid state going to water in the solid state. That is basically the making of ice. Yeah. And that is a physical change that is occurring. And we do definitely use sometimes chemical equations to represent physical processes that are occurring. And as you can see here, in this case, obviously we have the same sort of substance on both sides. The difference here is actually in the state. On the left-hand side is liquid water, right-hand side is ice. Obviously, the very last one, that is liquid water going to gas. Our steam, basically. And that's what happens at the boiling point when you boil water, right? Liquid water goes into steam. Steam is still H2O. It is the gas form of it, basically. And again, physical change happening. So, although most of the time we do look at chemical equations for chemical changes, we can definitely use them for physical sort of processes that occur as well. Other things that sometimes occur is sometimes up on the arrow, you may have some things written. For example, this is a physical process that is occurring. It's basically dissolving salt in water. So with water up there on top of the arrow, you're basically indicating that you're going to take the solid sodium chloride and dissolve it in water. When you do so, you will go from a solid sodium chloride to a solution of sodium chloride. And as you can see, that solution has the aqueous symbol next to it, which involves that it is a solution. Now, you may be wondering, by the way, if a solution is liquid and liquid is liquid, what is like the difference there between those two, right? So the idea there, if you have something in the liquid state or you have something in the aqueous state, they both are really liquids in the liquid state. The difference, though, is a liquid is typically a pure substance, while something that is aqueous is a mixture. And to illustrate that, if you took water, water by itself would be in the liquid state. It is just water, nothing else in there. But if you took water, like it shows down there, and you add some sodium chloride, which is a solid, those solid sodium chloride will dissolve, and now you will end up with sodium chloride that is a solution at that point. And it is a mixture. It's actually a homogeneous mixture. And a homogeneous mixture, right? Everything looks the same throughout. So basically, two or more things coming together where they retain their identity, you basically just made salt water, right? So that is really what aqueous is. It's really a homogeneous mixture where there's two or more things dissolved together in each other. As we'll talk about in a later chapter, the water in this case is what is commonly referred to as the solvent in the solution. And the sodium chloride would be what is known as the solute. And those are two parts that make up a solution when you put them together and stuff like that. So if you have something that is a liquid, it's usually just one thing by itself, nothing else with it. And again, something aqueous usually implies in a lot of cases you took something and you dissolved it in something else. So there's kind of a mixture of two things together. Other common things that you sometimes will see, for example, on top of the arrow, you may see a triangle written, and sometimes that refers to as heat being sort of added. Very common as well, up on top of the arrow, you will see a catalyst written. Yeah. And if you remember from chapter 10, a catalyst is not a reactant. It is not a product, and it does not get used up in the reaction. Remember that a catalyst is basically there to speed up the reaction. And if you remember from those energy diagrams that we talked about, there's that activation energy hill that they have to climb to get to their side. When you add a catalyst, it typically can find a much more efficient pathway of getting that reaction done, and it will lower that activation energy hill that they have to climb from reactants to products to get to their side, and that usually again will result in the reaction occurring faster. Any questions on that there? So again, sometimes you may see up on the arrow like an actual metal written like platinum. You may actually sometimes see like H plus written up there. H plus is an acid being used as a catalyst. So you'll sometimes see some other things sort of written up on the arrows on occasion. So now that we understand sort of the parts of a chemical equation, let's talk about sort of the process of balancing a chemical equation. And there's several different steps that you can follow. I'll be honest with you, most people kind of do like a trial and error type of deal, but uh, there's a couple of things you do want to make sure of. And one of the things you do want to make sure of is what I was mentioning earlier, which is if you are happen to be given everything in words and you need to turn those words into a chemical equation, the mistake that sometimes people make a lot is they try to write the chemical formula and balance the equation at the exact same time. And what they end up doing in a lot of cases is they will end up with the wrong chemical formulas. And again, like I said earlier, they'll be there all day trying to balance something that's never going to balance because you don't have the right formulas. So the steps that you want to always do is if you need to turn words into formulas, are probably where this happens the most is if you have the reactants given to you and you need to kind of write the formulas for the products, people always try to write the formulas for the products while they're trying to balance at the same time. And that's typically where things end up getting the wrong formula and not balancing. You want to always make sure that you start out with an unbalanced equation that has all the proper formulas. Just like if you were doing the nomenclature chapter and you were writing formulas for everything, you would want to get them all correctly down first. That is exactly what you want to do when you're doing an equation. Once you have all of them down, then you should roll to balancing. And you don't want to do those two things together. Never turns out well for people. I will say in a lot of cases, you probably will be given the formula with the equation with the formulas in an unbalanced state, but there will be some times where you'll have things in words that you got to turn into formulas. So once you sort of have all the proper formulas down, the first thing you want to do is you want to balance everybody. And remember that we can only change the coefficient in front when we're balancing. And you want to just pick up whatever seems, to be honest with you, there are a couple of different sort of ideas. You can start with the most complicated one and you can put coefficients in. I personally go with what seems just easiest to start to balance. It seems usually is a good move. And usually you'll have to put some coefficients maybe on one side. And then once you do that, you're going to probably mess up everybody else. You're going to have to put some coefficients on the other side. Sometimes you may have to start with putting numbers on both sides to actually just start the balancing part. But you want to continue kind of to use coefficients until everything is balanced. You have the same number of elements on each side of the arrow. And I will say at some point, if you're doing it correctly, things should kind of fall into place and you should end up with it being balanced and stuff like that. The last thing that you want to do is once you figure it out that it's balanced and you use all your coefficients there, you do want to make sure you have the same number of elements on each side of the arrow. And there's really kind of two things that you have to make sure of when you're done to have a properly balanced equation. Number one is all the coefficients need to be whole numbers. So when you are balancing an equation, all the coefficients need to be actual whole numbers. You can't have fractions, can't have decimals when you're all said and done. They all got to be whole numbers. The second is they need to be the simplest set of whole numbers. And what do I mean by that? Let's just say you had an equation and you balanced it like 2a plus 4b goes to 6c. And let's just say that this is a balanced equation. But when we look at the coefficients of 2, 4, and 6, we can clearly divide everybody by 2 and still have whole numbers. And this would not be considered a balanced equation at this point. We would want to basically divide everybody by 2, and that would give you a plus 2b goes to 3c. And that would be considered the balanced equation. So this sometimes happens because people could see larger numbers, and it is definitely balanced. You have the same number of elements on both sides. You just maybe use too big of numbers to balance it. So if you could reduce down all your coefficients by a common number, and the key there is still have whole numbers, you need to do that. And that is a very common sort of thing you want to make sure of. Any questions on that there? Here's another approach. And again, like I said, you could try this approach. You could try the other approach. We're going to talk about some approaches as we go through it here. But like I said before, I think most people really just start with, just kind of try a little here, try a little there, and kind of hope everything balances out. So let's take a look at an equation here and see how we go about balancing. So if I had this equation here and I want to balance it, this is how I would kind of take the approach. So I like to a lot of times use tables, and I think tables can be very helpful because it kind of organizes your thought process of where you might want to start and stuff like that. So for example, let me just rewrite this so it doesn't squeeze the numbers in too much here. Okay, just rewrite it. All right, so if I were to do this, I would make a table where I have the reactant side and the product side. And really, I would just list all the elements that are involved. So here we have nitrogen, hydrogen, and oxygen. And basically, I'm just going to do a little accounting of what I got going on both sides. So on the left-hand side, I have 1 nitrogen. On the right-hand side, I have 2. Remember that number goes to both. Guy to the left. On the left-hand side, I have 1 oxygen. On the right-hand side, I have 1 oxygen. On the left-hand side, I have two hydrogens, and on the right-hand side, I have two hydrogens. So I could clearly see from my table, I'm looking in not too bad shape here. Hydrogen and oxygen are balanced. So this also helps me decide nitrogen is probably the good place to start with, right? Because that's the only unbalanced element I got going on. So I'm going to balance the nitrogen here. And once again, we're going to use coefficients, the numbers in front to do so. So I'm going to go to the left-hand side, and I'm going to put a 2 in front of it, again, to balance it. Remember that when you put the 2 in front, it does count for everybody behind. So we're going to now have two nitrogens. We will also have two oxygens, and we still have our two hydrogens in this case. And as we see here, super common, fix one thing, mess up something else. But that's not a big deal because I can still refer to my table and I can see now that really oxygen is the only thing that's not balanced. So oxygen seems like a good place to go to. I would go to the right-hand side, and since I have two oxygens on the left, I will need two oxygens on the right. So I will have to put a 2 there in front of the H2O. Once again, this is going to go to both elements behind it. And that's going to give me on the right-hand side two nitrogens. 2 times 1 for the oxygen is 2. And 2 times 2 is 4 for our hydrogens. And now I can see from my table, I'm pretty much closing in on it. I got two nitrogens balanced on each side. I got two oxygens on each side. Now the only thing that's not balanced is my hydrogen. And again, I could go to the left-hand side and again, very simply fix that by putting a 2 there. And again, I'm going to have two nitrogens from here. I'm going to have two oxygens from there as well. And now I will have 2 times 2, which is 4. And now we have a balanced equation where once again, we have only changed the coefficients. This is as simple as we could get, although there's a lot of 2's there. If I divide everybody by 2, I will end up with a fraction for N2, which is not good. Yeah, so I can't go any smaller, obviously, than that. So this would be our properly balanced equation. Any questions on that? If the table helps you, do the table. If not, you might want to at least do the table at the end to make sure it is balanced. I can't tell you how many papers I've seen that people say they're balanced and they're not. So, at minimum, I would at least do the table at the end, and hopefully that might catch something for you if you need. All right, why don't you try one here? Let's balance up this one. So take a few moments there and balance it up. Take a look. Once again, I'm going to kind of make a table here. We got reactant side, product side. We got some carbon, hydrogen, and oxygen. Again, on the left-hand side here, we got 3 carbons. Right-hand side, we got 1. Left-hand side, we got 8 hydrogens, 2 hydrogens on the right-hand side. Left-hand side, we have 2 oxygens. Now, on the right-hand side, in terms of oxygen, we do have 2 here. We do not want to forget about 1 more hanging out over there. So that is 3 total oxygens in this point. And again, sometimes people miss the second one there on the far right. So at this point, when we look at it, we really got nothing balanced. And really, my approach would be what seems really easiest to sort of balance. And to me, it seems like carbon should be pretty easy. And I could balance carbon by simply putting a 3 over here on the right-hand side. Again, that 3 is going to go to everybody behind it. And that's going to give me 3 carbons. I will still have 2 hydrogens. Now, in terms of oxygen, we want to make sure we do this right. We got 3 times 2, which is 6 here. And again, we still have 1 hanging out over there, and that is a grand total of 7 on the right-hand side. Any questions on that there? All right, now at this point, obviously I fixed the carbon. I now have a choice here between hydrogen and oxygen as to which one I want to kind of go after. And at this point, I will actually go after the hydrogen first. And there is a reason why I would probably go after the hydrogen in this case. And that is because when I look at hydrogen on the left-hand side, it's only in one thing. And when I look at hydrogen on the right-hand side, it's only in one formula. When I look at oxygen on the left-hand side, it's on one thing. But when I look at oxygen on the right-hand side, it's in multiple formulas on the right-hand side. So when you have a situation like that, it's usually a good idea to kind of leave something like oxygen that's in multiple things on one side, maybe for the end, and rather than try and do that. Because clearly, if I do something with the obviously the oxygen on the right hand side, that may affect the three I already laid down there in front of the CO2 and stuff like that. So I'm going to attack the hydrogen because it's basically in one thing on each side. And to fix the hydrogen, I could simply put a 4 in front of it on the right. And again, that's going to go now to everybody behind it. That will give me 3 carbons still. 4 times 2 is 8 hydrogens coming here. And now for our oxygens, we still have 6 from our first one. And now we need to get 4 times 1, which is 4. And now that gives me a total of 10 for the oxygen at this point. And now I could very easily see I could fix the oxygen by going to the left. A lot easier probably than trying to do it first before the hydrogen, because now I got the hydrogen locked into place. And now I could go to the left-hand side and put a 5 there. And that's going to give me 3 carbons, 8 hydrogens, and 10 oxygens in this case. And now we have a balanced equation. Any questions on that? So again, I would highly recommend if you get a situation like that where you got to choose between maybe 2 elements, I would probably tackle the one that's in the least amount of things on each side versus the one that's in multiple things on each side, or at least one side and stuff like that. And kind of leave that guy for the end. Any questions there? Okay. All right, so let's try this one here. Write the balanced equation for the falling diboron trioxide reacts with water to form boric acid. So let's take a look. So in this case, we do have everything in words. So as I mentioned earlier, we want to make sure that we start with the correct formulas. So from our nomenclature talk, we have diboron trioxide. That tells us this is type 3. So that should be B2O3. Reacts with water, which hopefully we know is H2O. Forms boric acid here, BOH3 in this case. So once again, I'm not worried about the balancing or anything like that at this point. I just want to make sure I do get the proper formulas down first. Now that I have the proper formulas, now we could turn our attention to the balancing, and we're going to go BOH here. So 2 borons on the left and 1 on the right. We have 3 oxygens there. We don't want to miss that one. We do have 4 total on the left, and we do have oxygens here. This OH is in parentheses, and there's a 3 on the outside. That 3 does get distributed to each of the things inside the parentheses. So we're going to have 3 oxygens there and 2 hydrogens on the left. And once again, distributing that 3 into parentheses on the right will give us 3. At this point, not a lot to work with. Nothing's balanced. Definitely the easiest thing to balance at this point is the boron. And to do that, again, I would put a 2 on the right-hand side here. And we'll go 2 in front. That 2 does get distributed to everything behind it, including everything in the parentheses as well. So that's going to give me now 2 borons. For the oxygens, I have 3 times 1 into the parentheses, and then 3 times 2 onto the coefficient gives me a grand total of 6. Same thing with the hydrogen, 3 times 1 in the parentheses, and then 3 times 2 is 6. Again, that OH3 means that you have 1, 2, and 3 of those. And if you put a coefficient of 2 in front, you now have 2, 4, 6 of each of those things. Yeah. So again, you want to make sure you kind of count it correctly. At this point, I got my boron fixed, but my hydrogen and oxygen are not good. I clearly have nothing to work with on the right-hand side because I already put a coefficient there. And one of the things you probably typically don't want to do too much is start erasing coefficients, because then it makes it a very long day. So once again, I have a choice between hydrogen and oxygen. And in this particular case, you might think which one I'm going to go with. And the answer is I'm going to go with hydrogen. And I'm going to go with hydrogen here for the same reason as earlier. When you look at hydrogen on the left and the right-hand side, we see hydrogen in only one thing on each side. When you look at the oxygen on the left, it's in two different things and one thing on the right. So hydrogen is going to be much easier to fix first and save the oxygen for the end. So at this point, when I want to fix my hydrogen, I could just put a 3 on the left-hand side. That is going to get distributed to everybody behind it. And that's going to give me 2 borons on the left. I have 3 oxygens there, plus another 3 when I multiply it out over here. That's going to give me 6 oxygens, and 3 times 2 is 6. And what we see here is what commonly happens when you're balancing equations. I fixed one thing and it actually took care of both things for me, and everything else just kind of fell into place. Now I don't even have to worry about oxygen. It kind of self-corrected itself here by doing that. So again, when you have that choice, probably the better move is to attack the thing that is one place on each side. It's much easier. Any questions on that there? Yeah, let's try this one here, balance this one up, see what you come up with. Okay, so let's take a look at this one here. So once again, I'm gonna make a table. We got reactant side, product side. We have nitrogen, hydrogen, and oxygen. Left-hand side, we have 1 nitrogen. Right-hand side, we got 1. Left-hand side, 3 hydrogens. Right-hand side, 2. Left-hand side, 2 oxygens. And on the right-hand side, we also have 2, 1 in each. So everything looks balanced except for the hydrogen. And in this case, we actually need to put a number on both sides to begin with. Common number between 3 and 2 is 6. So we want to get everybody to 6, basically. So to get my hydrogens on the left-hand side of 6, I need to put a 2. Get my hydrogens on the right-hand side to 6, I do need to put a 3 in this case. And again, distributing our kind of coefficients to everybody behind will give us 2 nitrogens. We will have 6 hydrogens and still 2 oxygens. On the right-hand side, 1 nitrogen, 6 hydrogens. We have 1 oxygen there, and we do have 3 times that, which is 3. That's a grand total of 4. Once again, I'm going to look for sort of what's easiest to fix as I fixed the hydrogen and messed up everything else. So nitrogen definitely looks easy to fix. All I have to do is put a 2 in front of the nitrogen. And that again is going to get distributed behind. That's going to give me 2 nitrogens on the right, still 6 hydrogens. Now in terms of my oxygen, I have 2 in the first one, and I have 3 still in the second one. So that is 5 at this point. So at this point, we have everything balanced but the oxygen. We have a couple of options here. One option is we can just go to the next problem. No, I'm just kidding. We can erase coefficients, which seems like a very bad idea. So what we basically need to do in this situation is we have 5 oxygens on the right, and we only have 2 on the left. We need a way to turn our 2 on the left into a 5, since that's the only open spot to do so. And one way that you could do that is you could actually use something like perhaps 5 over 2. And if I use a fraction like 5 over 2, I will now end up with 2 nitrogens. I still have 6 hydrogens. And when I take 5 over 2 and times it by 2, they cancel. And that leaves me 5 in this particular case. And now I do have a balanced equation. Problem, though, is with my balanced equation is that coefficient is not a whole number. So you will oftentimes come across this when you're balancing an equation. Sometimes you may have to use a fraction to balance an equation, and that's perfectly acceptable to use a fraction to balance an equation. What is not acceptable is leaving the fraction. So you have to clear the fraction when it's done. So this would not be considered a properly balanced equation, but we do need to get rid of the fraction. And to do that, we would multiply everything by the denominator, the guy on the bottom. So we'd multiply everything by 2, and that would give us 4NH3 plus 5O2 goes to 4NO and 6H2O. And if I did not screw up, I should still be balanced. So just to check, I got 4 nitrogens on the left. I got 4 on the right. I got 4 times 3 is 12 hydrogens on the left. 6 times 2 is 12 on the right. I have 5 times 2 is 10 oxygens on the left. And over here I have 4 oxygens. And over here I have 6 oxygens, which is 10. And we are balanced in this case. So this illustrates a good point that you can use a fraction to balance it, but you do need to get rid of the fraction. Now, sometimes people go, I'm not really sure what fraction I should use. Well, there's a very simple formula for the fraction. If you remember, the number we needed was 5. So the number up on top should always be the number you need. And the bottom number should always match the subscript. So it should always match the subscript. And you'll always pick the right fraction. So up on top, the number you need. Bottom should always match a little subscript there to the right. Everything will cancel out correctly, and you will always have the right fraction. Any questions on that move there? Yeah. All right, another sort of thing in terms of balancing that you sometimes come across is an equation like this, which has a lot of stuff in it, and maybe you would want to just skip over it. And when you have an equation like this, I personally would perhaps take a different approach than what I would do on the previous ones that we did, which is more the table approach. So here I would probably take, like I said, a different approach. And the reason for that is there's a lot, especially in this one I wrote here, there is a lot of polyatomic ions stuck in these formulas. And you absolutely can do a table like we did and kind of do each element individually. But if you do that with the parentheses and stuff like that, you're just going to have a lot of multiplying in and multiplying out. And there's probably going to be a bigger shot of maybe an error along the way. So sometimes when you do have an equation where there's multiple polyatomic ions on either side of the arrow that are the same, it's a lot of times a lot better to keep those together and just kind of balance the polyatomic ions on each side rather than go like how many nitrogens and oxygens I have. So for example, if I were to sort of take this approach here, and you could really start with sort of either one in this case. One might be better than the others in this case, since we have a choice of 2 polyatomic ions. So let's just say I start with the nitrate, and I look at the nitrate over here, I got 2, and I look at the nitrate over here, and I have 3 of them. And once again, the common number between 2 and 3 is 6. So I'm going to turn my nitrate over here into a 6 by putting a 3. I'm going to turn my nitrate over here into a 6 by putting a 2. Now, when I do so, what I might want to do next is sort of figure out where I want to go next. Now, I know that I need a 2 for my aluminum, right? So I could go over here and simply put my 2 there because once I change that first number, it's going to change the second. And now I have 2 aluminums, and I also have 6 of my OHs. And now I could come over here to the right-hand side and go, oh yeah, when I did the number for the nitrate, I also changed this guy's number to a 3. So I will need a 3 here. And at this point, I should be balanced in that case. And a lot of times what you want to do is balance the polyatomic ion. And whatever is attached to the polyatomic ion, that's really where you want to go next. So, and as we can see here, we have basically 3 magnesiums on each side, 2 aluminums on each side. We have basically 2 times 3, which is 6 nitrate, and 3 times 2, which is 6. So if we take a look at, say, this top one here, just to kind of show it to you one more time. Again, on this top one, I would go for the sulfate, and I could do that because I do have sulfate on each side, and it's exactly the same. And when I start with the sulfate in this case, I now have 3 on the left and only 1 on the right. So to fix the one on the right, I'm going to put a 3 there. That's going to give me 3 sulfates on the right to match the 3 on the left. Now, in this particular case, we only had 1 polyatomic ion on each side. And what you would want to do in this case is, because I changed the 3 for this guy, I also messed up the calcium, and that's where you would want to go next. And since I did 3 for the calcium, I need to go to the other side and put a 3 for the calcium there. And when I do the 3 for the calcium, that's going to now give me 6 chlorine, and that's where I should go next. and I go to the right-hand side to get me 6 chlorine, and I need to put a 2 there, and that gives me 6 chlorine. That gives me 2 iron, and I don't have to do anything because I already have 2 iron. So a lot of times if you have polyatomic ions, it's much, much easier to keep them together. And in a situation like this last one, if you have just one polyatomic ion or whichever one you start with, if you only put a number on one side, then you want to go to whatever that's attached to the other side, put a number there, and then whatever that's attached to, that's where you kind of want to go. So why don't you try the last two here to finish up on balancing here? Balance these last two equations. Let me actually write the bottom one there a little higher there. We'll go C4H10 plus O2, CO2, and water there. All right. So give this one a go and give this one a go. Okay, so since we're kind of getting to the end here, let's take a look at these together. I'm going to actually start with the second one first here, the one with the polyatomic ions. And again, I can see I have nitrate here, and I do have nitrate over here. I actually do have phosphate here, and I do have phosphate here. Now, again, you can choose either polyatomic ion to start with, and one might work out better than the other. So just to show you that if you choose the wrong one, it's not a big deal. I'm going to start with nitrate, which actually is the wrong one. I'm going to show you why I know it's the wrong one really quickly. Here I have 2 nitrates, and I only have 1 here. So when I go on to fix my nitrate and I put a 2 here, that is going to give me 2 nitrates, but it will give me 2 coppers, which is not good because, you know, I got a 3 there. So you could either fix it at this point by trying to figure out what it is, or, you know, you could just try your eraser, and since you only put one coefficient down, start with the other polyatomic ion, right? So if we start with the other polyatomic ion, I'm going to actually start with the phosphate. And with the phosphate here, I have 2 and I have 1. Now I'm going to put a 2 in front for my phosphate. And that's going to give me 2 phosphates. That's going to give me now 6 coppers. I always want to say carbon. 6 coppers. And that's really where I should go next, because that's what was attached to what I fixed. Because this was attached to where I fixed, I can go to the right-hand side. And now I'm going to be okay, because now I'm going to put a 6 there for my copper. And since I put a 6 for my copper, that will now give me 6 nitrates. So now I know when I go to the other side to fix my nitrate, I actually need a 3 there to give me 6. And that gives me 3 bariums, which once again, as I said, eventually everything should kind of fall into place. And that's exactly what we need on the other side. So if you started with the nitrate in this case, you could probably very quickly figure out maybe it's not the right one. You could actually fix it if you did that. For example, we put a 2 here, and that gave us 2 coppers, and but we had 3 over here. So you could basically multiply those numbers together and get 6 and figure out, oh, 6 is actually what I need here. And you could actually fix it. Or you could just go back and restart, kind of like what I did. Any questions on that one there? Now, for this last one here, we're going to go back to the table method again, because there's really no polyatomic ions. And really kind of keeping everybody together is really better for like a polyatomic ion situation. If you don't have it, probably the table method is a little bit better. So we got 4 carbons on the left. We got 1 on the right. We have 10 hydrogens on the left, 2 on the right, 2 oxygens on the left, and 2 oxygens there, plus 1 more there is 3. So once again, I'm just going to take the easiest thing to fix, which to me is carbon in this case. And I could put a 3 in front of my carbon. That again is going to get distributed. So that's going to give me 3 carbons. We will still have 2 hydrogens. Now in terms of oxygen, I do have 6 here, and I do have 1 here, which gives me a total of 7 on that side. Now, again, I have a choice between hydrogen and oxygen, and much like I've done on previous examples, I am going to go with hydrogen because it's only in one spot on each side. Here again, we have oxygen in a lot of places. So to fix the hydrogen, I can simply put a 5 there, which will get distributed, and that's going to give me 3 carbons, 10 hydrogens. Now, in terms of my oxygen, I still have 6 here, but now I got 5 times 1, which turns this into a 5. And that is a grand total of 11 in this case. Now, everything is balanced except for the oxygens. And once again, we're at that situation where we definitely don't want to erase coefficients. Really, the only thing we could work with is what's on the left, and we basically got to turn that 2 into 11. So this again is a fraction situation, which would be a good move. Once again, to do the fraction, I need 11 on the left. That is what should go on top. And what should go on the bottom is the matching number there, and that should be 11 over 2. And at this point here, I will now have 4 carbons, 10 hydrogens, 11 halves times 2 should give me 11 oxygens in this case. And at this point here, we should be balanced, but we do have to clear the fraction. So once again, to clear the fraction, we need to multiply the entire thing by the denominator in our fraction. And we're going to multiply everything by 2. That will give us 2C4H10. That will give us 11O2. That will give us 6CO2 and 10H2O. And once again, this should still be balanced. We got 8 carbons on the left. We have, I messed that really bad actually because I went with a 3 instead of a 4. That was a terrible choice, wasn't it? Nobody's like, hey, maybe you should do a 4. No? All right. Ignore all that right there. That's like a misstep very badly. We'll fix it in post-production. It'll be all right. There we go. I'm going to try that again. All right. So clearly you want to pick the right number to start with, like a 4 there would be good. So, all right. One more time with filling here. Let's try it again here. All right. So originally a 4 would be a much better choice there because that would give me 4 carbons on there to match my other. And obviously that's going to give me here 2 hydrogens. We have 8 there and 1 there, which would give me 9. At this point, we could continue on with our hydrogen, which I think is still a 5. And we would then have 4 carbons. We would have 10 hydrogens. And now we will have, how about 13? Close. So 13 over 2 would be a winner for our fraction. Once again, the number up on top is the number we need. We're now going to still multiply by 2. And now we will end up with 2 plus 13O2. I could say, I was just saying if anybody was paying attention, which clearly nobody was, right? Or I could just say I screwed up very badly there. Let's hope we come out better here. That's now 8 carbons on the left. There's my 8 on the right. We now have 20 hydrogens on the left. We got 20 on the right. In terms of oxygen, we got 26 there. We got 16 there and 10 there. 26. Any questions on that there? I get simple numbers, hard to handle. All right, let's wrap that up for today before